In 2022, the NASA Psyche mission will launch an orbital observation satellite to perform imaging, magnetometry, and other scientific research of the Psyche asteroid, which orbits between Mars and Jupiter. While this mission will be strictly orbital, it is not beyond imagination that a return mission may be conducted to land on the surface. As such, our team has been commissioned to develop a robust and adaptable landing system to deliver a research payload safely to the surface. Enter the Kinetic Energy Rebound System, a prototype rebounding landing system designed by our team at Michigan Technological University. In previous microgravity landings, the anchoring system has been a common point of failure, leading to undesirable rebounds that may jeopardize mission success. To address this, our team has decided to take a radically different approach and create a system that utilizes rebounding to its advantage, requiring no anchoring at all. Our design uses collision dynamics and energy transfer to create a controlled rebound scenario. By absorbing the potential energy of freefall into compression springs, there is a moment in time where the velocity of the payload is essentially zero. We release the package at this moment, leaving it safely on the surface while the rest of the lander springs away. Removing the external MLI coating reveals some of our key design features, such as the main thrusters, used for powered descent from orbit, the attitude adjustment thrusters, used to orient the craft normal to Psyche's surface, the pyrotechnic release pins, which allow for pinpoint accuracy in payload deployment, and our compression springs, which are the focal point of this rebounding design. Our concept has been verified through multiple avenues of testing, such as hand calculations and physics simulations, bench testing, all culminating in the drop test of our 1/5 energy scale prototype. Through our design and testing process, we have proven the feasibility of this concept, which has never been attempted before for space landing applications. At the completion of our testing, we have identified several areas in which our system could be improved. For the prototype, improvements to material strength could combat fatigue due to cyclic loading. Upgraded control system hardware will allow for increased sampling rate and release accuracy. Continued implementation of realism into our simulated models via energy losses, mass updates, and material properties would help prove scalability.